So this talk is, as you see, oh, I forgot my glasses. As you see, is about propositional proofs as characterizing them as non-commutative formulas. So it's very, it will actually encapsulates, combine several, two of the talks before by Tony and Pavel. But I will repeat some of the arguments, or mainly the definitions. Yeah, and it's a joint work with Fu Li and Zhengyu Wang. They are PhD students in these places currently. So let's start just with a sketch of the result. So the result that I'm going to present is this: lower bounds on non-commutative formulas. And we've seen this model, I think, in at least a generalization of it. It was ABPs, algebraic branching programs with, but there it's non-commutative, namely the order of multiplication. So the ABPs, each layer, the order of multiplication when you go through the layers is important in non-commutative branching programs, and I'm going to speak about non-commutative formulas, but most of the results here actually also hold for ABP, non-commutative ABPs. So the sketch is this: lower bounds on non-commutative formulas for certain polynomials gives us lower bounds on Fraga proof sizes. This is a Fraga proof. It's not extended Fraga, it's Fraga, it's important. And I will give the precise definition of what is a Fraga proof. This is one direction of this implication. The other implication also holds, although we lose here, it will be a quasi-polynomial increase in size when we want to simulate the system. So let's start just with Fraga proofs. So I think this talk will be quite, hopefully quite easy, because there's not a lot of proofs. There's just definitions, and they are very basic. I will try to cover them thoroughly as I can. So what is a Fraga proof? So we've seen what is certain kinds of propositional proofs, and this is presumably the most popular one, which is taught in, someone said, high school. So this is it. It's just any, let's say the following: any standard textbook proof system for propositional tautologies will hold here, because this Fraga proof is a notion which is very robust. So any two systems with the definition that I will tell you in the next slide will hold, but I want to make it concrete, because a lot of people are always confused about what is the actual definition of a proof, of a Fraga proof. So this is so we start from axioms and derive using derivation rules and axioms new tautologies, all written as Boolean formulas. So we have only this 4 lines in the proof system. This is a complete definition of a Fraga proof. There are 3 tautologies, which are axioms, and 1 modus ponens rule, right? So B implies A, this something about negation, and this something about implication, and that's it. And then we have modus ponens. If I know A and A implies B, then I know B. Now, these are everything that we need to know. This is Fraga, but it's obviously closed under substitution. So when I mean that we have these axioms, I mean that every substitution instance of these axioms, we have them, right? And also the modus ponens. So this is Fraga. It's very easy to define. And also note that it's important in complexity that this is like I write it as a formula. I write it like as a tree. You can consider it as a tree. And this is an example of Fraga proof. So I have this axiom I instantiated with only one variable, right? X. And then I have this axiom. So here You can check that this is indeed a proof. I have this axiom. This is it. B here is x implies x. I use modus ponens. I get this one. I use another instantiation of this axiom. And then from modus ponens, I get this. So this is a Fraga proof. This is all you need to know actually about Fraga. So you see that this is very simple to define, but actually to work with it is very cumbersome. You see, even the simplest things are quite hard to derive, but it's good as at least to give the definition, which is concise. So yeah, so this proof, we can consider it, and I will consider it as the graph of the proof, or the underlying graph of the proof, because in this case it's just a tree. Every node has a formula. Label it. Okay, any questions? No. So let's see this. Frege system is complete and sound. So obviously I used only implication and negation, but I can also, it's a complete basis, connective, logical basis. So I can actually say and, I can say with this. So it expresses, can express and prove all tautologies. So it's complete because it can prove all possible tautologies in negation and implication. And it is sound because the rules, the axioms are tautologies, and the rule is sound. So by induction on the proof length, you can prove that everything that is in the bottom, in the root, is indeed tautology, right? So it's complete and proof sound for all possible tautologies written as formulas with this basis of implication and negation. And that's it. That's Frege. It's like it's very simple. Now this is an observation which seems trivial, but it's in some sense important to us. So assume I have everything is syntactic in Frege. So everything is just a term, really a syntactic object. So if I write x and y, and I wish to actually derive y and x. So these are, in Frege, these are two different, at least in the definition that I gave, these are two different terms. So I really need to do a derivation to actually implies or to commute y and x here. And this will play some role in our result. That commutativity, we really need to work for it in Frege. So we need to explicitly derive it, and obviously by completeness there's a constant size proof of at least of this, but if there's a bigger formulas, so it will be like a linear maybe proof in the size of the commuting terms. Okay, so this is Frege, it's complete and sound. And so still when I say this to people, people still say, but what is the actual definition? You gave me just an example, so I decided to put, this is the most general definition that actually encompasses all possible Frege proofs. It's this, the formal definition is this. It's just a set, finite many rules. Obviously, if it's infinite, it's meaningless because I can put all tautologies. So it's finite many rules closed under substitutions, right? I substitute formulas in this X, and I have A1, AK implies or derives A0. K is again a constant. When k is 0, I say it's an axiom, because from nothing I can derive this. So this is a set of rules. You can see that, and the rules are closed under substitution of formulas. So you can already see that the concrete example I gave is indeed a Frege proof. It just has axioms and one rule, 3 axioms and 1 rule. So it's precisely, this conforms to these requirements. And a Frege proof is a DAG, directed acyclic graph, whose sink is f, so I prove the tautology f at the root, and each node is a formula derived from its incoming nodes by a rule, or it is an axiom. Either it is derived by its incoming nodes or it's an axiom. And we require, this is something a bit technical, so we also require strong completeness or implicationally completeness. It's not extremely important for us, but for the formal definition, we need that if there are assumptions and they logically imply F, then we must have a Fraga proof of F from the axioms. So it's not just tautologies, it's also complete from assumptions. So that's the general definition. Now, so here is an example. Now we go to complexity and we ask what is the complexity. We've been discussing this all day. What's the complexity of proofs? The usual measure is this, the size of the proofs, like in algebraic circuits, what is the size of the circuit? So here the size of the proof will be, I just count the number of connectives and variables. So it's just the sum of the total size of all the formulas in the proof. So I just counted it, and it's 41. So this is the complexity of the proof is 41 symbols. And that's it. Now, so here the example is a tree, but as I said, we can have this as a DAG, meaning that from this axiom I can also have other lines coming from it. So, but we'll see that I will mention that as a result it says that it's not important if it's a DAG or a tree in this setting of Frege. Actually, Tony already said this. So, and as we've discussed today, can we prove a super polynomial size lower bound on Frege proofs? Major problem in proof complexity. So, prove that there is a family Fi's of tautologies such that no polynomial is bounding the proof, the minimal Frege proof of Fn. Right? So, I want to find an infinite family of tautologies such that there is no polynomial that bounds the minimal size in this Frege proof of this Fi. So it's a super polynomial lower bound on Frege proofs of a certain family of tautologies. So we've discussed this. I just fixed the definitions, and now I'm going to speak about the algebraic model of non-commutative formulas. So I think we've already seen this. As I said, Michael talked about ABPs. But they were, so you said that these are read once ABPs, and it's actually identical, it's equivalent to non-commutative ABPs, right? So but I will talk about formulas, not ABPs. It's a bit weaker, I think. I'm not sure there is a separation, but it's not known yet. So let's define it again. Fix a field F, for instance, rationals. Non-commutative functions are like this. So I will talk about non-commutative polynomials and non-commutative computation, meaning that the product is non-commutative. So it's x times y is different than y times x. Think about it as plugging in matrices, right? 2 by 2 matrices. So the product is non-commutative. That's how we want to compute non-commutative functions. But it's over some field, right? It's a base field. Now, here is the non-commutative formula. It's just a tree where we have product and plus and the output and the input here. And every time we have a product, we record the order because x times y is different than y times x. So that's it. That's non-commutative formula. And it computes the non-commutative function x, y minus 2yx. Now I will discuss also f. When f is gf2, it looks a bit weird because if f is gf2, then f is commutative. Obviously, actually any f is commutative. So the point will be that this f can be commutative, but so you can think about this as the matrices are non-commutative. They are over gf2, but their scalars are just 0, 1. So it's okay. Sorry? There are inverses for the matrices. There are. Not every matrix is invertible, so it's not everything has inverse.
There's no inverse operation.
Oh, sorry.
Addition and multiplication. You can inverse field elements, but there's no divisions of the non-scale.
But actually, Amkip Gam speak about those skew fields.
Oh. But there's no division here, and also there's no. Not every matrix will have you can have plug in the zero matrix. Now, but it's not a good example. So this is a non-commutative formula, and we just count. Sorry, we count the number. I have disobeyed the orders. We count the number of formulas. The number of nodes here. So this is, I think it is not completely trivial, to do the balancing of formulas. I don't think it was known before Wigderson and Hrubesch and Wigderson who proved it. For non-commutative formulas, they proved it with non-commutative formulas with division. We show that by inspection it's the same if there's no division. So formulas, non-commutative formulas can be balanced. It's important it will be important for us. I will not show you precisely why, but in one of our simulation will use the fact that everything is balanced. So this we already know, non-commutative formulas, what it is, and we've discussed a lot in the first days in the boot camp. Lower bounds on these models. So we have exponential lower bound on non-commutative formulas from Nissan. It's just the rank method that Michael talked about. We've seen the partial derivative method. So we know an exponential lower bound on this, and thus I say it's kind of a weak model of computation because we have a lower bound on it. And it's also not a very complicated lower bound proof. So let's go to the main theorem. So I showed you what is a Fraga. I showed you something which is seemingly unrelated, a non-commutative formula. And let's see that in some sense, these are, from the complexity perspective, these are very, very similar objects in the following sense. So there exists a natural map between tautological formulas T to non-commutative polynomials P, such that the following occurs. If T has a polynomial size Fraga proof, then P has a polynomial size non-commutative formula. So this is very nice because it shows that if I take a tautology, and we talked about searching for lower bounds, if I take a tautology, I take the map and transform it into a non-commutative polynomial, a single non-commutative polynomial. If I can prove a lower bound on this non-commutative polynomial in the non-commutative formula regime, then I get a Fraga lower bound. Well, what I said is not precise because actually we don't get a single polynomial, we get a family of polynomials which are semi-explicit. That's the catch. If we had one polynomial, it might be much easier to prove regular bound. And actually this is a simulation that I will prove. It's not extremely difficult. The converse is very tedious to prove, a lot of results, and it take a lot of time to actually get all the details done. But we have the following. That's why I say it's non-commutative or characterizes Fraga. So P has a polynomial size non-commutative formula. If this P we can compute it with the non-commutative formula over GF2 here, and this T also should be a DNF. Then Fraga has a small proof, but here we lose a bit, so it's not polynomial simulation, it's quasi-polynomial. So Fraga will have an n to the log n proof of this T. Uh,
Natural map needs to have an inverse.
oh, a natural map needs to have an inverse. This way to say it, it's a bit maybe not natural to say it, but it will be just an IPS characterization following Groucho and Pitassi's work, and I will show it next. So there exists a map. It's not completely unexplicit, but it's also not completely explicit. This quasi-polynomial increase is an artifact of several factors. I don't think it's very critical. I think it can be reduced. It depends on only one thing. It depends on the fact that homogenization of formulas, not circuits, is done by Raz 4 years ago or 5 years ago. It was done with a quasi-polynomial increase in size. While we've seen the classical homogenization constructions are just in polynomial size increase if it's for circuits. But if it's for formulas, it's a bit more involved to do it, and you get some increase in size.
For this, you don't need Raz, right? That's just you can think of formula as a circuit, do the circuit, and then convert it back to a formula. What I'm able to show it for 4 degrees, not that.
You're right. You're right. Yeah. Yeah. That's that. Yeah. After we simulated Raz, we have seen that we actually don't need it in our case. But anyway, we had this. It was a nice result to show that Fraga can actually simulate this Raz construction. Right. You're right.
How does this transformation depend on the degree of the polynomial?
How does this transformation?
Does the size and to the log n does it become if the polynomial p is really low degree, but
if it is a low degree, then you can simulate. Oh, sorry. If it is a low degree, then you can simulate it. If the proof is of low degree, then I would guess that you can simulate it. Then anyway, there's a short proof anyway.
by low I mean I still need little omega 1.
The power is little omega 1.
Log n or so. Do you get? Does the trade-off give us a better bound there? Like n to the O of log n, does it become poly n for some degree?
Yes. It's written in the paper that you're right. It's written in the paper that if you have a lower degree, we actually get a better bound, I think. Yes. So that's the result. And the argument is a characterization of Fraga Proof as I define it as a single non-commutative formula. And this is done by introducing a non-commutative version of the IPS that we've seen last hour. And it's the work of the IPS defined by Groucho and Pitassi in 14. And this will be a non-commutative version of this. So let's just do the proof of the simulation. And for this, we need to look again on the IPS, or the non-commutative version of the IPS. So let's just fix this. So let's assume we are talking about CNFs, and we want to encode them as low-degree polynomials as before. So if I have these clauses, if I have these clauses, this is unsatisfiable CNF, right? It's 3 clauses. And I turn them into non-commutative polynomial equations. So for me, it will be non-commutative. It's 1 minus x1, x2. This is the translation, the standard one. This will be equal to 0. These are the constraints that will be equal to 0. And so 1 is satisfied by a given 0, 1 assignment if and only if 2 is satisfied by this given 0, 1 assignment. But this I consider them as non-commutative equations. And in fact, these I will consider them as non-commutative formulas, right? So this is how I describe the formulas. And this is the non-commutative ideal proof system, IPS. IPS is just this, non-commutative. So it's non-commutative IPS, it's this. I start from axioms or constraints, which are non-commutative polynomials in the x variables. There are n variables here. And I will say that also these are non-commutative polynomials, or written, for instance, as non-commutative formulas. And these are, I constrain them to be 0. And I will also assume, just for simplicity of writing, that the Boolean axioms xi times y minus xi for every I, and these axioms that I will talk about are in this set. Just for simplicity of writing, the axioms are actually in the set. So I don't know if you remember the IPS definition of Groucho and Pitassi from that Pavel talked about, but it's almost the same, except the following thing. So we added the following axioms, the commutator axioms, that says that xi times xj minus xj times xi for all pairs of variables equal 0. Yeah, this should be also, yeah. So these are our axioms. This axiom in some sense says that we are working over 0-1 solutions, and this comes because we need completeness. This is the only reason we need it, completeness. It's easy to show that it's not complete without. It's not easy, but it's possible. Sorry.
That goes against non-commutativity.
Sorry?
That goes against non-commutativity.
It goes against in the moral sense. I mean, what do you mean? Yeah, it is. The point is that we want to restrict it to 0-1, but what is the?
You want to count the number of times you use commutativity. Okay. You also want that to be in the
It's not. It's also this. Also, without this, it's not complete. Of course, then you can think about it as commutative polynomial, which will be complete in this sense. But then you would not have a it will not be a proof system where you can verify in polynomial time. So the idea here is that if we allow this and we really force the user of the prover to use these axioms in order to get, and this is the same as before, in order to get a big polynomial in the x and the placeholders yi's, such that if we put here zeros, it's 0. It's in the ideal generated by the y's. And if we put here the axioms fi's instead of the y's, then it's formally equivalent as a non-commutative polynomial to 1. Then because it's formally equivalent to 1, and using these axioms, then via Rasen-Spilka result from 2004, we have a way to check that that this equality holds.
So you also need placeholder for the new axioms, right? Not just for the files.
Yes, so I said that for simplicity, these are actually fall here. Yeah, so I didn't put them here. But again, from Rasen-Spilka, this is what is called a standard proof system, a Cook record proof system, because it's checkable in polynomial time, deterministic polynomial time.
What is the null length for non-commutative system?
I don't know, but I didn't find it. There is maybe some restricted versions.
But here you don't need it.
We don't need it because I will show you a completeness result, which is not very hard. It's just by simulation.
When it comes to the final equations, it's still it's still over a commutative. It's just that you're also accounting for the number of times you use commutator.
So, this is also over arbitrary field F. So you can think about it as I said, as over matrices, F algebra of matrices. So you have F, and the algebra is of D by D matrices with the entries from F. That's it. So, I don't know if any non-commutative non-standard sets there are.
There is no non-commutative non-standard that you need for.
Oh, in this case, you don't need. Okay, it is complete because of these axioms. It's the Boolean axioms. It will be complete, at least for. Yeah, it's for everything. It will be complete because it just simulates a polynomial calculus. Okay, any question? So this is the non-commutative IPS, and I claim that this, why do we need this axiom? As I said, it's for completeness. For instance, how can I refute this? This is over 0, 1, it's equal to 0, right? So it's unsatisfiable. But how can I refute this in the system without this commutator axioms? I cannot do it. So I need this for completeness. Yeah. So let's just prove everything now, the easy theorem. Why it simulates Frege. So we start from these axioms. Yeah. So we start from this CNF. Let's talk about CNF again. It's the same CNF. Let's just first show an example of how this proof system works. So if I have these constraints and 1 is satisfied by a given 0, 1 assignment, if 2 is, then what is the non-commutative IPS refutation of this? This is a very simple case because I just add all the axioms and assume that this is also one of the axioms. So if I add this plus this plus this plus this, then I get precisely 1. Notice that if I didn't have this, everything would cancel except x1, x2, x2, x1. Which is not cancel, that's why I need this. So this is the IPS refutation of this CNF. And because I have this placeholder, this idea of Groucho and Pitassi, I want to actually consider it as a polynomial in the x and y's. So the only variables I use are actually the placeholder for the axiom. So it's just, this is the polynomial. It's just y1 plus y2, y3 plus y4. This is the polynomial that this, let's say, CNF maps to. Okay, I will use a slightly different definition now for the proof. So, yeah, so that's what I said. It's Razin-Spilka proof that it's we can verify, and this proof is checkable in polynomial time. So how can we prove that non-commutative IPS simulates Frege unconditionally? So this was a difference between this and the conditional result of Groucho and Pitassi. So this is how we do it. We start with a Frege proof if we've seen before, just 4 axioms and rules. And we use the following translation of Boolean formulas to arithmetic formulas. So now think about this a bit informally. Just take a Frege proof, it's a tree or a DAG of formulas, and just do the obvious thing. Just translate with this standard translation that I think Pavel used, or used slightly different, but it's almost the same. X goes to X, false 0, true 1, or 2 times, and negation to 1 minus translation. So take the, yeah, the or is times in this case. You can do it, it's dual for the other way. So, sorry. So you just take a Frege proof with these formulas and just use this translation on every line. Every line becomes an algebraic formula, because if I have or, I translate it into times and so forth, right? So let's assume here we have implication. So let's assume implication is actually shortcut for not A or B. So we do this, we have a tree, we just transform everything to arithmetic formulas. It's almost done. We just have to complement things here because it's not precisely a Fraga proof, so we'll add some more rules and we complete the proof so that it will be really an arithmetic proof with sound algebraic rules. I will show you in a minute. But I'm just showing you here informally. So there's not a lot of work. You just take a Fraga proof, arithmeticize everything, and that becomes what I will call polynomial calculus over arithmetic formulas. But it's easier to use algebraic inference rules instead of the logical inference rules. Instead of these, let's use algebraic rules. And the point is that this work was already been done by Grigoriev and Hirsch. So, but let's see the first attempt for algebraic version of Frege. So as I said, so we have a Frege proof, we transform it into arithmetic formulas, but I wanted to say it's easier to work with rules which are algebraic, not logical ones. And the rules here, as Tony discussed, are plus and times. Here it's such a simple proof, then there is no times even. So it's just plus. So the proof that I will get is this: 1 minus x1, x2, there's one constraint, another constraint. I add them, I get this polynomial equal to 0. I have this axiom, right, from this, and I add these two, and I get 1 equal to 0, meaning that this is a refutation, because this is like false. This is like the formula false. Sorry. Sorry. Yes, I'm now talking about the I'm now talking about how to take Frege and work it out with commutative formulas, right? I will show you in a minute how to go to the non-commutative version. But now I'm just translating Frege into a more simpler way, into an arithmetic regime. So this is how I do it. It's very simple. Now, but there is a catch here, a small thing, that here it's not a syntactic term. I just plus them, and instead of doing syntactic manipulation on the formulas, so I just wrote this as this. If I add these two polynomials, I have infinite many ways to actually represent this polynomial. But I took here a small version, just x2. So I want, and as I said before, in Frege everything is syntactic. And this relates directly to what Pavel talked before about syntactic manipulation of arithmetic formulas or circuits. So I'm not just, and this is why it's just the first attempt, because this I will not have a way to verify that this was legitimately implied by this plus, right? I need to syntactically do it. And that's why, this is what it says here, and that's why it's easy to fix this. The idea that Pavel talked before about, I just use rewriting rules that simulate the commutativity, distributivity axioms and zero axioms and all these syntactic manipulations. So I will have a proof system that has plus and times of two lines, and times for any arbitrary line, and as before, but also within a sub-formula, I can do rewriting steps like this. If I have a formula in the proof with t, inside it there is a subtree with t times s, I can replace it with s times t. And this was this is how it is. Let's see an example. So the formal proof of the informal proof in the last slide, this is the formal way to do it. I just add these, but this becomes just a syntactic term. I rewrite here, meaning that I use distributivity. It's a simple manipulation of formulas. I open the brackets here, and then I do something which I don't even know. Oh, yeah. I have done something, but maybe there's a typo here. Oh, I commuted this term and it became x1, x2. And then this becomes, I distribute -1, and then this becomes 0, and then 0 times something is 0 by rewriting rules, and I get syntactically to this term. And this is the polynomial calculus over formulas by Grigoriev and Hirsch. So it's just polynomial calculus. We consider arithmetic formulas and rewriting rules. And they show that this is possible. We've seen the intuition. It actually simulates Frege. So all we need to do now is simulate via the non-commutative IPS this algebraic proof system, which is easy. PC over, so this is the formal definition for those who like it. So there is of this system that I just talked about. It's two rules: addition, multiplication, and product. Yeah, if I have this equals 0, then I can derive xi times f equals 0. And I have the Boolean axioms, and I have all the rewriting rules which actually are applied inside formulas. For instance, I have commutativity f times g. I can replace it to g times f. And I have all the other unit rules and so forth. It's precisely the same rules that Pavel talked about. And PC over formulas is just the DAG whose sink is f. And each line is either an axiom, the Boolean axiom, or was derived from its incoming node by one of the two of the rules, addition and product, or it was derived by a rewriting rule inside the formula. That's it. So that's what this is, the system that we, and this can simulate Frege. It's probably even stronger than Frege. At least it's more expressive than Frege. So we want to simulate this with one big non-commutative formula. It's not extremely hard. First, we take the following theorem, structural theorem by Krajcek. I actually don't know who. 5 minutes. Yes, sure. So Fraga proofs, DAGs, can be transformed into proof trees with only polynomial increase in size. It's handy to know that, that Tony said already, that in Fraga proofs or anything above resolution, tree proofs and DAG proofs are equivalent up to polynomial increase. So we can assume, without loss of generality, that and this transformation, because the simulation of Frege by Grigoriev and Hirsch transformed a tree-like Frege into a tree-like PC over formula proof, then we can actually assume that our proof, that PC over formula proof, that we want to simulate with non-commutative IPS, is a tree-like proof. So we start with the tree-like proof, and that's it. We almost finish. Small PC over formulas proof, this is the Grigoriev and Hirsch, of G implies small non-commutative IPS proof of the translation of G. And I said, what is the translation? So it's actually by induction on proof length. We construct the non-commutative formula based on the skeleton of the arithmeticized propositional proof, also something that Tony talked about. It was the circuit, right? It's almost the same, the circuit, the Hilbert proof. It's very similar. Let's do some cases. It's not hard. So case 1, the product rule. So if I have in my original proof, I have G implies some circuit, some formula G that I have derived. Now I want to use the product rule and say, if G equals 0, then xj times G equals 0. So I have G implies this. So what will I do in the non-commutative IPS? By induction hypothesis, I already have a proof P with the X plugging in my axioms F1 to Fm. In this case, these will be only the Boolean axioms, by the way, but forget about this. So I have this, and I know that this equals G, and it's of small size. It's size polynomial in the proof, in this proof. by induction hypothesis. And then what I do, I just add, this is the circuit that I built, the non-commutative circuit that I built. I put here product, and I put here the tail xj. And that's it. That's how I construct it by inductive on the structure of the proof. Yes, so I have, so this should be like probably in the other side, sorry. Yeah, sorry. So yeah, if this is, right, because everything is syntactic, so this should be to the other side, but on the other hand, because it's actually flipped, so it's actually correct if you transform it. So, so yeah, but this is correct comment. So we define this, and we have obviously xg. Now, what else? So case 2, the addition rule is similar. Just add these two, and rewrite rule. So here we have some luck because we don't even care about them. Accept the commutativity rewrite rule inside the commute terms, inside formulas, so they actually don't change the polynomial computed. So we don't care. So forget about them. We have only to deal with the case 4, commutativity rewrite rule, and this, it's a bit another induction on the size, how to use the commutator axioms to actually take two formulas and commute everything inside them. It's another induction. And that's it. So we finish the simulation, and this is why Fraga is simulated by non-commutative IPS. Now we have the other direction. This is almost the last slide. The other direction is a bit harder. And the proof, I will not show you the proof. It consists of many simulations, uses many structural results in algebraic circuit complexity like RAS, but as Samir said, it's not, the RAS in this case is not completely necessary. And it uses, the most dominant ingredient is a simulation in Frege of RAS and Spielka PIT for non-commutative ABPs. And this took a lot of work. From the logical perspective, the idea is just a reflection principle for non-commutative IPS. So we just prove the following. Inside Frege, we prove this big formula that says if F has a non-commutative IPS proof, then F. We can prove this in Frege, and these are the conclusions and open problems. So one conclusion is, I just said this, something that it's slightly interesting. Every non-commutative polynomial identity over GF2 of size S has actually a quasi-polynomial in S Frege proof when considered as a Boolean tautology. So every identity, if we take a non-commutative identity, it actually has a Frege proof when we consider it as a Boolean formula over GF2. And of course, the open problem is, can we prove lower bounds on non-commutative IPS and thus prove lower bound on Frege? We might hope that because non-commutative polynomials are more easier to handle, to prove lower bounds because we have this rank measure, then it might be easier or much more easier to prove lower bounds there than to prove for Frege from the original Frege proofs. There's a lot of other open problems, but I didn't write it down. That's it, I think. Yeah, that's it. Any questions?
I have a question. So the translation, you said that from going from P to P, you said it's not very explicit, and it seems pretty explicit. So